Welcome, ladies and gentlemen, to my presentation about switching the work function of the organic-inorganic interface tetrachloropyrazine on platinum 111. Let me start the presentation with quickly going through the title, starting with switching the work function. Well, here you can see a metal and a Fermi level and a vacuum level, and that defines a work function. Now, if we absorb a layer of molecules on top of this metal and there is, say, some charge transfer that goes to the molecules, we get an interface dipole, and this interface dipole leads to a shift in the work function, and this gives us a new work function. And this has been the focus of many studies where people tried to design specific work function shifts. What we want to do is go one step further and make this shift changeable once the molecules have already been adsorbed. To do so, we use the system of tetrachloropyrazine on platinum 111, which forms two different adsorption states. One of these adsorption states is the on state, where the molecule is chemisorbed, and the other is the off state, where the molecule is physisorbed. With these two adsorption states, we can form different classes of interfaces. For instance, we can place only off-state geometries onto the surface, forming an off-state interface. We can mix both, forming a mixed-state interface, or we can form an on-state interface. Now, by looking at the individual adsorption geometries, we can already learn something about how the molecules are going to be arranged in the different interface structures. Now, before we do that, let me quickly talk about the different molecular arrangements I'm talking about. For instance, the molecules may arrange into a commensurate structure where the unit cell of the molecule layer is a supercell of the substrate. The next type of structure would be a point-on-line structure where the molecules sit on lines. The lines neatly fit onto the substrate, but within the lines the molecules don't follow the periodicity of the substrate. A higher order commensurate structure is similar to a commensurate structure, with the difference that the unit cell of molecules that fits onto the substrate contains a larger number of molecules. And finally, we get an incommensurate structure where we can never find common boundary conditions that satisfy both the adsorbate layer and the substrate. Now, to determine the adsorption energy and other properties of all our interface structures, we use periodic boundary condition based density functional theory. And this requires commensurate structures. So what types of structures do we have to deal with? Well, if we look at the on-state adsorption geometries, we find that the molecules are strongly bound to a specific site on the substrate. So moving the molecule across the surface gives us a deep potential well, and that makes it likely that the structures that on-state geometries form are commensurate. On the other hand, the off-state adsorption geometries are bound via van der Waals interactions, and these interactions are not very site-specific, so the molecules have a shallow potential well when it comes to moving them across the surface, which makes it easy for molecules in an adsorbate layer to adjust their position to benefit from molecule-molecule interactions. And this, in turn, makes it likely that incommensurate layers form. So we have to deal with incommensurate structures, which puts us into somewhat of a predicament because we're really bound to commensurability, just like the little guy you can see in this cartoon called the rusted technocrat, who is only capable of drawing commensurate structures, and in fact he has drawn himself into a cage. And it turns out that we are stuck in a commensurate cage as well, but what we can do is we can make the cage larger. And what I mean by this is that we can approximate incommensurate structures by using higher order commensurate structures. So we take a commensurate structure, stretch the molecule layer or compress it, and that gives us a higher order commensurate structure. And we allow up to 100 molecules per unit cell, which makes the structures too large for density functional theory to deal with. So we're going to have to use some machine learning, but more on that on the next slide. Before that, however, let me briefly talk about the different structures that we are considering. The first set is an exhaustive list of commensurate structures, which we generate with the sample approach. The sample approach is something we have developed and published, and it requires the adsorption geometries I've been talking about earlier and a set of unit cell, and with that it can generate all possible structures within some boundaries, of course. In addition to those, we use higher order commensurate structures, which we get by taking the best commensurate structures and running them through a simulated annealing algorithm, and that gives us higher order commensurate structures. In total, this gives us a couple million different possible structures, which is clearly far too many to deal with density functional theory, so we are going to use machine learning to find the properties that we're interested in, and we're interested in the energy and the work functions. This requires some training data where we calculate energies and work functions with density functional theory for a couple hundred structures, some prior knowledge, and then we put this into a Gaussian process regression algorithm, and that then allows us to predict energies and work functions. So let's look at some results, starting with the adsorption energy, which is given on the y-axis in electron volts per nanometer squared. The x-axis shows the coverage, and in the plot you can see all the energies of the on-state structures. The red line shows you the lower convex hull, and the shaded area behind it is our prediction uncertainty. And we find that the energetically most favorable on-state structure has a coverage of about 1.6 molecules per nanometer squared. If we now superimpose the off-state structures, we find that the energetically most favorable off-state structure has a coverage of about 1.8 molecules per nanometer squared, and that it also is lower in adsorption energy. And this really demonstrates that off-state structures can benefit from molecule-molecule interactions, as I said previously. And looking at the mixed-state structures, we find that they lie in the middle of on and off-state structures, as we would expect. Now, the fact that on, off, and mixed state structures have the energetically most favorable structure at the different coverages allows us to think about using thermodynamic conditions to switch between these structures and thereby switch the properties of the interface. And the way we do this is by using the Gibbs free energy of adsorption, which you can see here. Now, the Gibbs free energy of adsorption is what a structure wants to minimize. Now, Gibbs free energy of adsorption, gamma, is given by the coverage theta, and by the adsorption energy of a molecule and the chemical potential of a molecule in gas phase. And there would be some more terms, but these are usually neglected in literature, so we do this as well. And if we now have two structures, structure 1 and structure 2, where structure 1 has a larger coverage than structure 2, we find that initially, for a lower chemical potential, the Gibbs free energy of adsorption for structure 2 is smaller than that for the more densely packed structure 1. And for higher chemical potential, we find a phase transition, and then the more densely packed structure 1 is more favorable. If we now plot the structures with the lowest Gibbs free energy of adsorption for different temperatures and pressures which go into the chemical potential, we find a phase diagram like this. On the y-axis you can see the partial pressure of the tetrachloropyrazine molecule, and on the x-axis the temperature. Now, for a low temperature, we find that an off-state structure has the lowest Gibbs free energy of adsorption. If we increase the temperature, we find a mixed state structure, and right on the right hand side of this plot at about room temperature, we find that an on-state structure is lowest in Gibbs free energy. Now, if we go from a mixed state structure to the on-state structure, we can switch the work function by about 300 millielectron volts. And to give you an idea of how large this number is, the threshold voltage of a germanium diode is about 200 millielectron volts. Now, there is one further thing that we need to consider, and that is that at a finite temperature, there is a finite probability for structures other than the one with the lowest Gibbs free energy of adsorption to occur as well on the substrate. So if there is a larger area, we find a mix of different polymorphs that give us a mix of different properties. And this is shown on the right-hand side, where you can see a more smoothed out plot. Still, the quality remains the same, so we go from off-state structure to mixed-state structure to on-state structure, but now the amount of work function by which we can switch the interface has decreased to about 200 millielectron volts. But still, this is in the range of the threshold voltage of a germanium diode, so it is certainly something that one could measure and maybe even technologically utilize. And with this, I would like to conclude my presentation. I would like to thank my colleagues, acknowledge funding agencies and computational resources, and of course, I would like to thank you for your attention.